Okay, so hi everyone, and nice to meet you. My name is Adi. Thank you very much for inviting me to talk. I was registered into this workshop solely to study and to learn from you, the experts. And I wish I could be there in ECT Star. So thank you also for accommodating this remote talk. So as I've said to Ethan and to the organizer, this talk you can consider it as a call for help. As we really need to implement a more sophisticated model for our radiative correction in the projects that we're working on. So what I'll do in the first part of the talk, I hope it will be quick. I'll just browse over the motivation that we have. Then I'm going to dive into the implementation that we've done already for a very simplistic model of radiative correction. And then I'm going to ask for your help and recommendations and maybe open it to discussion. Okay, so we're coming from the field of neutrino oscillation, as was seen in Sasha's talk yesterday. We're learning the oscillated flux of that is coming from neutrino accelerators. They're incoming to our detector, interacting with the nucleus, and many particles are shooting out. And we are very used to measure those outgoing particles, to apply the interaction model, and to reconstruct the neutrino energy, which is the one thing that we care about. To extract the oscillation parameters. Obviously, the big challenge lies in this interaction model that is very complicated. And many things can happen when the neutrino interacts with the nuclei, quasi-elastic interactions, of course, but obviously also more complex processes. And with the final state interaction, reconstructing the neutrino energy and modeling that correctly is a big challenge. Okay, this comes even more pronounced and more important when moving on to the next generation of experiments that is expected in the next decade. So on the left, you can see an example from an historical plot from T2K. There we had to just extract the height and the width of the first oscillation in order to get the mixing parameter. Now, when we're moving on to what's going to come from example from Dune, on the right hand plot, this is of course simulated events. We would like to get this oscillatory picture. As you can see, we're moving into higher energies. As you can see, the differences between the x-axes. And also we need to be a lot more precise when extracting the incoming energy to make sure that we're not smearing this oscillated picture and extracting or getting a bias in the mixing parameters. So if I can summarize this, I think also Sasha has used this in his talk yesterday. We're measuring the number of events in our experiments, but this is actually a convolution of the true incoming flux, which we want to measure, and the modeling input, the cross-section, and the smearing or transfer matrix between reconstructed and true energy. And there are many ways to deal with it. We can improve theory, we can use new detectors, and what we're doing specifically in our project is to use electron scattering as external constraints. Okay, so I'm going to do the PR for our project called Electrons for Neutrinos, where we're using electrons to constrain those models that are being used for neutrinos and trying to reconstruct the incoming energy of the electron and to test that method. Okay, so why we're using that? Obviously, because there are similarities between electrons and neutrino interaction. The identical initial state, the incoming or the hit nucleon or nucleon's momentum are the same if the incoming lepton is a neutrino or an electron. Sorry for the noise from the outside. Also, the final state interaction are the same, and there are similar interactions, though not identical. So it's true that in the electron case, it's the electromagnetic interaction with only the vector part, and in the neutrino case, it's the vector plus axial due to the weak interaction. So using the electrons will not be enough to constrain the models, but it is a very, very good test because any model that aims to describe the neutrino model or interaction with the nuclei must by definition also describe only the vector part. Okay, also electron beams have very known energies, so it's a good method to test our energy reconstruction. And there's this asterisk that we really need to account for the differences between neutrino and electron, and one of the differences is of course radiative effects, which we have to include in our analysis. Okay, so the premise is very simple. We'd like to analyze the electron scattering data to use that the results to improve the models and to tune the parameters within this model, and obviously to determine the implication on neutrino oscillations. In the neutrino world, we have some event generators with the potential goal of describing not only quasi-elastic or not only deep inelastic scattering processes, but all of the processes. I gave you two examples of GENIE and GEBU. Of course, we have more, Euro and Newt, but these are just an example. They're all working using factorization of the interaction. First, taking into account the initial state, or modeling it, then each interaction mechanism separately, whether it's quasi-elastic, meson exchange, resonances, or deep inelastic scattering, and then adding on top of that final state interaction. And then there are differences between different event generators. If there's consistency between the initial state and the final state interaction using the same potential, or if it's completely factorized. So there are a few differences, but the overall idea is similar. Most of these models are empirical or semi-classical, and some, most of them are also phenomenological, but with many free parameters which can be tuned. There are also empirical and semi-classical models for some of the processes, and they could really use constraints from external data. Okay. So the first thing we've done in our project is to make sure to validate the consistency between the electron and the neutrino modes of the generators, and we're specifically working on GENIE, which is vastly in use in the US. So here you can see, for example, one of the models, the superscaling implemented in GENIE, the comparison between energy transfer and Q3 in the electron mode on the left and the neutrino mode on the right. We've done many of these plots. Of course, we need to scale the events to account for the difference in the propagator. But with that scaling, we see that relatively we're looking at similar distributions. In our project, we're working with data from the class detector. So I'll briefly go over it because it will be important also for the radiative correction, the radiative effect handling that we're applying. Okay, so we're taking data that was collected in class at JLab. The experiment already ran 20 years ago, but we already collected the data from its upgrade, class 12. But let's talk a bit about class 6, the old generation. To this detector, electron beam was aimed with energies up to 6 GeV. Obviously, it has large acceptance and low detection threshold that are comparable to those in neutrino experiments. And it's kept a lot of data already 2 decades ago, and we're now diving into it. So here's a summary of the targets that we were using: helium, carbon, and iron, and the energies we were using 1, 2, 4 in GeV. Again, this is just for reference, but we're gonna go and check out what we've done in the results. I think here I've added I needed to mention class coverage. We said that it's very wide, but it's obviously not complete. So you can see on the sketch here that there are 6 sectors, and here on the left the acceptance map with respect to the polar and polar and azimuthal angle, and you can nicely see the 6 sectors. I've mentioned that because we were focusing in our first project on quasi-elastic-like events. So we chose events with 1 protons and no pions above detection threshold at the final state. We chose that because it was the simplest thing to do as a first go. And also this signal is commonly used in neutrino oscillation experiments. We thought that reconstructing the energy in quasi-elastic-like event would be fairly simple. But of course, there are non-quasi-elastic contribution to this selection of 1p0 pi. And not, I mean, for the coverage in class, for the acceptance in class, we can correct, and we've made acceptance correction. But also the processes are, I mean, there can be multi-nucleon interaction or resonance interaction, and then final state or particles that are going below a detection threshold, looking like a quasi-elastic event, which are actually not. And this is what we really want to nail and to make sure that we're modeling properly, again, to make sure that our oscillation experiments are not biased. Okay, so now we've arrived to the radiative effect, as we said that this is critical to take into account when we're comparing electrons and neutrinos. So because we focused on quasi-elastic-like events, and most of our events were actually quasi-elastic, we took deliberate into using the simplistic model for radiative effect that is being shown. I think also Axel in his talk on Tuesday mentioned it. This is very similar to what was done in CMC for JLab. So we took into account initial and final state radiation only for the electron side and some loop corrections, again, ignoring the proton side, and implemented inside GENIE the basic MONSI, and then later using some of Van der Hagen methodology in order to implement it into an event generator. So again, we used this for all of the processes in GENIE, which we know is wrong, but because of most of our events were quasi-elastic, we thought that it will pass. And we got radiative corrections of up to order less than 2%. We validated this model using electron scattering on hydrogen from JLab. So here you can see in red default GENIE without any radiative correction, and in blue GENIE plus the radiative correction that we've implemented. Okay, you can see that it's nicely giving us the detail with when reconstructing the incoming energy of the electron. And so we were pleased with or encouraged by this validation, but that was not enough. We also tried to minimize the effect of radiation in our event selection. So for this plot, I need to show you first class coverage. So what we've done is we vetoed the event with a photon close to the final state electrons. And here you can see the difference between the final state electron and a photon in the same event. The difference between their angles. So we really just cut all the events with a photon next to the electron. And also we vetoed the event with the outgoing final state lepton energy that was very small. We assumed that most of the energy was lost due to radiation. So both of these cuts, plus correcting for the event generator, for radiative effects inside our event generator, we marked this topic as covered for the quasi-elastic-like analysis, and we looked at the results. Okay, so this is a workshop on radiative effects. I'll just browse through one result to emphasize the importance of this project to us. If you want more, there's in the backup I can show, and of course you can ask me later. But then I'll just browse through this real quick as an example, and then I'm gonna give the stage to the questions that we have, and hopefully have a discussion. Okay. So again, just an example for results and the impact they can have. This is the reconstructed energy of the incoming electron with events with one electron and one proton and no pions in the final state by summing the energy of the electron, the proton, and adding a binding energy. So you can see in the data points, the class points for incoming energy of 1 GeV, and the dashed and solid line are two models that are in use in GENIE, also being used for neutrino studies. Okay, this frame is just a magnification of the tail. Okay, so you can see that there's a difference in the peak. One of the models just gets the peak wrong, and also there's a difference in the height, and there's a difference in the tail. And again, we're using these events in the neutrino mode to get the oscillated picture. this basically means that we're really smearing our oscillated picture, and we need to model that properly. And this is a summary of all of the reconstructed energy in all of the energies, 1, 2, and 4 GeV in different columns. And you can see on top electron scattering on carbon, and on the bottom with iron. So there is a lot of information here. So I'll draw your attention to the differences in the tails. So you can see that as you go higher and higher in energy, the difference in the tail becomes pronounced up to a factor of 2 in the higher energies. These are going to be the energies in future experiments in neutrinos. And also the difference in the peak that is not consistent, the height of the peak. And again, in one of the models, we're getting the binding energy wrong. This is really the call for us to improve our models and to refine them. But we need to make sure that we're doing this properly, and not only for quasi-elastic events, we're accounting for the radiative effects as we should. Okay. Again, there are many results, but I'm sparing you, and if you're interested, please reach out. Next step is to dive into more complicated processes. So here you can see multiplicity plot, because in class we can see not only just one proton, we can see many protons and many pions. So there's an ongoing analysis. You can see here for looking at final state of 1 proton and 1 pion. We already started an analysis looking at 2 nucleons, either 2 protons, or first look at 1 proton, 1 neutron, which is really a first for neutrinos. And okay, you can see here also several inclusive results in double differential. But here really, I'm raising our need in order to dive into more exclusive and non-quasi-elastic interaction, especially 1p, 1pi, or 2 nucleons. We really need to make sure that we're accounting for the radiative effects. And again, this is a call for the experts to see if it's feasible in the next or in the coming future to account for it. If there is no model for specifically meson exchange and resonances, and no way to account for the interference in the radiative effects between the proton and the pion, or the 2 protons, and can we think of smart cuts to minimize the effects, or can we at least assign a systematic if we're not accounting for it? And obviously, I hope that it will increase the motivation, because once we'll implement this for the electron mode, which is important for our project, of course, we intend to use the same machinery to do that for the neutrino mode as well. And all of the, we hope that we can use some of the calculations that have been presented in this workshop and other studies, okay, for the benefits of the experiments. Okay, so I'm going to leave this slide on, and maybe just thank you for your attention and for the opportunity to present here. And I'd be very happy to get either questions or thoughts.
Okay, thank you very much, Adi. Let's thank the speaker.